Black, heavy, often deadly. This is what can happen when a large aircraft... The fire has burned less than 2 minutes. It is unique in its magnitude, its intensity, and the speed at which so many people are suddenly involved. This is only a test. While it is true that major aircraft accidents occur infrequently, each small emergency should be considered a potential major accident. Every effort should be made, therefore, to fully protect occupants in any emergency, large or small. The station should be capable of housing the equipment to protect it from the elements, the personnel assigned to man the trucks, and an area suitable for training. There are two 1,500-gallon water foam trucks, as well as a tank or nurse truck to provide the water needed to augment that carried on the water foam trucks. At this station, for instance, there is a dry chemical truck, often referred to as a light rescue truck. This lightweight dry chemical truck carries a complement of tools for use in forcing entry into an aircraft. This truck, shown schematically, carries 500 pounds of dry chemical extinguishing agent. The dry chemical agent is highly effective for extinguishing electrical fires, engine fires, or small spill fires. It can also help in containing larger fires, pending arrival of the water foam trucks. Nitrogen, used as the propellant, flows into the dry chemical chamber, fluffs up the powder, and is the force used to expel the agent. The 500 pounds can be discharged in 1 minute. Here at a test site, the use of dry chemical is demonstrated by trainees. They approach the fire from upwind. Nozzles are held waist high, slightly elevated, to obtain a minimum discharge reach of 20 to 30 feet. For maximum results, the nozzles are moved slowly from side to side. But since dry chemical cannot provide the blanket required to completely extinguish a major fire, foam is required. These water foam trucks are the mainstay for extinguishing a major fire. The solid stream from the truck turrets is used in the initial approach to a fire. With proper use, it should have a reach of not less than 135 feet. The solid stream can quickly cool a fuselage and suppress adjacent fire. Then a wider blanketing action is obtained by using a dispersed stream pattern. While this has the advantage of providing a blanket about 35 feet in width, its reach is limited to about 60 feet. The water foam nozzles, therefore, have the dual capability needed in extinguishing a major fire, the capability of cooling and blanketing. Let's see briefly in a schematic view how the water foam system functions. This tank holds about 180 gallons of foam concentrate. And this tank holds 1,500 gallons of water. A suction proportioner combines the water and foam concentrate in the desired proportion. It is fed at a rate of 800 gallons a minute into the turret. Here in the turret, air is then combined with the solution, expanding it about 10 times, thus providing a discharge of roughly 8,000 gallons of finished foam a minute. As soon as the main fire is knocked down, the turret discharge should be curtailed. Each hand line discharges about 600 gallons of foam a minute and is used to extinguish fires in areas inaccessible to the turret streams or in mopping up after a large fire has been suppressed. Remember, The agent carried on the trucks is the only supply that can be depended upon, so use it wisely. But remember, equipment is only a tool. Its effectiveness is dependent upon the capabilities of the men, the firefighters who man the trucks. Training sessions should be conducted daily. When seconds are of paramount importance, reaction of the firefighter in fighting a fire must be both automatic and correct. In this session, for example, the instructor is showing the way trucks should be deployed in approaching the burning aircraft outlined on the board. Remember, wherever possible, take advantage of wind direction and terrain. The lightweight truck, usually the first to arrive at a crash, should be positioned so that the agent may be used effectively in suppressing or containing the fire. When its extinguishing agent is expended, the lightweight truck should be moved, when necessary, so as not to interfere with the approach of the two water foam trucks and the tanker. During approach, the turrets on the water foam trucks are actuated about 100 feet from the fire's leading edge. Initially, solid streams are applied to provide the reach necessary to cool the entire fuselage. Within seconds, these solid streams are then directed to suppress fire adjacent to the fuselage, gradually extending the distance between the fuselage and the fire front. The tank truck provides backup support for the water foam trucks with its additional water supply. The trucks move in to further suppress fire along both sides of the fuselage. At this time, the turret discharge is changed from a solid stream to a dispersed pattern. This permits covering a wider area and reduces the probability of disturbing the existing foam blanket. In the initial control of a major fire, hand lines have only little value and, if used, could be a needless waste of extinguishing agent. When attacking a major fire, the full fire suppression potential must be used, but the agent should be conserved, as the only dependable supply is that carried on the trucks, and this can be expended in possibly a matter of minutes. Besides fire suppression, firefighters must know the location of exits and procedures for opening them on all aircraft using the airport. With the fire suppressed sufficiently to permit evacuation, emergency chutes at exits can be released by the aircraft crew. When required, the emergency exits located over the wings may be used to expedite evacuation. In addition to daily classwork, each man must thoroughly know his equipment so that its use is automatic. Now let's see how well-trained firefighters used their equipment in an actual emergency. We are at Washington National Airport. The tower controller alerts the firefighting units.
Attention, please. This is the tower. United 705, a DC-7, returning to Washington, and will be landing runway 18, number 4 engine out. Stand by on the field.
Remember, each aircraft emergency is a potential major fire. Where time means everything, valuable seconds are saved by promptly alerting the firefighters, who can then take their positions at predetermined locations. This one happened to be a fire in number 4 engine, which started when the engine froze. Pumpers responding from a nearby community lay a hose line from the nearest hydrant to the site of the emergency to supply additional water if necessary. By quickly blanketing the engine with foam, the fire is promptly extinguished. The success of this operation was made possible by pre-planning, training, and the proper application of foam. Aircraft passengers were safely evacuated. Now let's examine a new procedure which the FAA tested and proved to be the best method to assure passenger survival in a major aircraft fire. This method followed our formula: reaching all parts of the fuselage, keeping it cool, and blanketing the fire area. The test site, FAA's Experimental Center at Atlantic City. A pad 200 feet in diameter was specially prepared. Two 5,000-gallon tanks on the elevated earth mound at right contained JP4 fuel. A manually controlled metering valve regulated the flow of fuel to 4 outlets, extending 6 to 8 inches above pad level. For each major test, a transport-type aircraft, C-97, was positioned between the fuel outlets. Each aircraft was insulated so that it would be thermally equal to a modern air carrier. 78 instruments installed inside and outside the aircraft recorded vital data. This included aircraft skin, interior and exterior air temperatures, and toxic gas concentrations within the cabin areas. Rates of fuel flow for the major fires were established at 200 gallons the first minute, 500 gallons the second minute, and 1,000 gallons a minute for the succeeding minutes of the specific test. A grid of 10-foot square units was marked on the pad so that the geometry of the fire could be observed accurately. It is July 1964. The test you are about to see is presented just as it happened. Never before have test fires of this magnitude been available for study and analysis. All is ready for fuel flow to begin at exactly 2 minutes after 2 o'clock. It will flow for 15 seconds before ignition. And there's the torch off. Fuel is now flowing at the rate of 200 gallons per minute. This simulates an aircraft accident in which initially a single wing tank was ruptured, spilling fuel under the aircraft. Fire fed by fuel which is constantly being replenished and increased to simulate an actual accident condition is a flowing spill fire which is more difficult to suppress than a static spill fire. 45 seconds after ignition, the flow of fuel is increased to 500 gallons per minute, simulating the rupture of additional fuel tanks. Notice the increase in fire area and intensity. It is now 70 seconds after torch off. About 450 gallons of fuel have flowed. Firefighting commences. A solid stream discharge is used first. Let's see it from the air. A minute and a half after ignition, the trucks move closer to the fire area. Now the dispersed pattern is used from the turrets. This provides wider foam coverage and lessens the tendency to break the foam blanket. Ground sweeps are actuated to suppress fire under the wings. The flow of JP4 fuel is increased now to 1,000 gallons per minute. This rate continues for the 5 minutes remaining of this test. Notice that the fire intensity and area is not materially increased when the flow rate is doubled. This is because a large portion of the burn area is covered by the foam blanket. The fire is no longer influencing temperatures within the aircraft. Evacuation paths are clear. The turrets are now cut back to a single barrel stream to conserve agent. The fire is under control. Once a decision is made to go into a dispersed pattern, the solid stream should not be used again unless reach is essential. You see, when a solid stream is used at close range, it may break the integrity of the foam blanket already laid. At this point, 2 3/4 minutes after torch off, Instruments show that temperatures within the aircraft cabin do not exceed 150 degrees. Foam blankets of about 2 inches in depth are effective. Increasing the depth of the blanket can be a waste of agent. It is 3½ minutes after torch off. Fuel is still flowing at 1,000 gallons per minute. 2,200 gallons have been fed to the fire. Remaining fires at the outlets and on the periphery of the fire area will probably not endanger aircraft occupants or hinder evacuation. At 4¼ minutes after torch off, turrets are shut off. The small finger-like fires, now visible, can be extinguished by the action of the foam, which flows like heavy cream and will seal the exposed fuel. The use of hand lines here may scatter the foam blanket, exposing a larger fuel area, thereby intensifying the fire. At this point in the operation, the hand line men can assist in occupant evacuation. It is 4¾ minutes after torch off. 3,500 gallons of fuel have been fed to the fire. Fuel will continue to flow for the next 2 minutes to equal the maximum quantity normally carried on a large jet aircraft when landing. This demonstrates that when additional fuel is fed to a fire area well covered with a foam blanket, the fire area or intensity is not increased. The ground sweeps continue in use to maintain the foam blanket around the fuel outlets. Throughout the entire 7-minute test, cabin temperatures did not exceed 120 degrees, except in the aft section of the aircraft. Temperatures in this area rose to 180 degrees, but were gradually reduced to 120 degrees as foam was applied. Lethal levels of toxicity were not even reached. So, by the prompt and intermittent application of foam on the fuselage to cool the metal and blanket the fire area immediately surrounding the fuselage, it was possible to maintain a livable condition within the cabin until the fire was completely extinguished. As you can see, the fuselage is still intact. Rescue paths parallel to the fuselage could be quickly opened, and every passenger could have been evacuated before the fire was completely extinguished. Remember, it is the saving of life that is of paramount importance. To review briefly, the use of hand lines was ineffective in the initial control of this fire, and in some cases caused considerable flame flare-ups, which could cause injury to passengers evacuating the aircraft or firefighters working in the area. The use of ground sweeps was not required to protect the firefighting equipment, but they were effective in suppressing fire under the wings and in containing the fire surrounding the fuel outlets. It was the solid streams from the turrets that quickly cooled the fuselage and first covered the adjacent area with a foam blanket to rapidly suppress the fire. Then, the use of a dispersed pattern quickly widened the foam blanket, thus providing a greater separation between the aircraft fuselage and the fire. Equipment needs and effective techniques are determined through such test fires and studies covering aircraft evacuation procedures. Aircraft firefighting and rescue units, so equipped and so trained, can provide the protection recommended today. While minor emergencies do occur frequently, days, months, or years may go by before a major fire occurs to challenge the well-equipped and trained firefighters. They live daily with the thought that when a major accident occurs, they only have seconds to show their ability, how well they know each piece of equipment, and how thoroughly they have absorbed their daily training in the classroom and in action drills. It is only through such extensive training that firefighters can gain confidence in the equipment and the experience necessary to perform effectively. They are ready for major accidents in this, the challenge of the jet age, regardless of frequency. When every second counts, when every drop of agent is needed, it is the automatic reaction of the firefighter that is important. He must bear in mind three things: reaching the length of the fuselage, cooling it, and blanketing the fire area.